Welcome to Chapter 8, Internal Flow. In this part of Fluid Mechanics 1, we shift our focus to the flow of fluids confined within boundaries, such as in pipes, ducts, and channels. Internal flow is all around us, from water running through household plumbing to oil circulating through engine systems. Unlike external flow, where the boundary layer can develop freely, internal flow is significantly influenced by the presence of solid walls that fully enclose the fluid. Understanding internal flow helps us design efficient piping systems, minimize energy losses due to friction, and predict pressure drops accurately. We'll explore key concepts such as laminar and turbulent regimes, velocity profiles, entrance lengths, and head loss. This chapter lays the groundwork for applications in HVAC systems, chemical reactors, and microfluidics. Let's dive into the world of confined motion and uncover how fluid behaves when it has nowhere else to go but forward, guided and shaped by the walls around it. Introduction to internal flow. Internal flow is all about motion within boundaries. Picture water rushing through a garden hose or steam moving through industrial pipelines. This type of flow happens when a fluid completely fills a conduit and moves primarily due to pressure differences. The entire space is sealed off, no open surfaces, no atmospheric contact. It's important to recognize that internal flow is different from open channel flow. Open channel flow, like in rivers or irrigation channels, is only partially enclosed and driven mostly by gravity. In internal flow, the key driver is pressure. Our main concern in this chapter is pipe flow. That's where we analyze how fluids lose pressure along the length of the pipe, what we call head losses, and how much energy is required to overcome those losses using pumps or compressors. These principles are not abstract. They're used every day in real-world systems for heating, cooling, and moving fluids in everything from homes to chemical plants. So as we study pressure drops and power requirements, remember, mastering internal flow is essential for designing efficient thermal fluid systems. 2. Laminar and turbulent flow. When fluids move inside a pipe, they don't all behave the same way. Sometimes the motion is calm and predictable. Other times it's chaotic and messy. That's where the concept of laminar versus turbulent flow comes in. Laminar flow is smooth and streamlined. It's like layers of fluid sliding past one another in perfect order. This happens at low Reynolds numbers, specifically when RE is less than 2300. The motion is stable, with minimal mixing and no sudden changes in direction. Turbulent flow is the opposite. Here the fluid swirls, fluctuates, and creates eddies. It's unpredictable and energy losses are higher. Turbulence kicks in when the Reynolds number is above 4000. In between these two extremes, we have the transition flow region, an unstable zone where the fluid keeps switching between laminar and turbulent states. To classify flow type, we use the Reynolds number, Re, which is calculated as rho Vd divided by mu, where rho is density, V is average velocity, d is diameter, and mu is viscosity. It's a powerful, dimensionless number that lets us predict behavior based on flow conditions. For ducts that aren't circular, like rectangular or annular pipes, we replace diameter with the hydraulic diameter. It's defined as 4A over P, where A is the cross-sectional area and P is the wetted perimeter. This allows us to extend our analysis to a wide variety of engineering systems. 3. Entrance region. When fluid first enters a pipe, it doesn't immediately behave the way we expect in the middle of the system. Initially, the fluid flows with a uniform velocity profile, flat across the cross-section. But as it moves forward, viscosity starts to act. This slows down the fluid near the walls and gives rise to a developing velocity profile. This evolving behavior is caused by the formation of a boundary layer, which grows thicker as the fluid travels downstream. Eventually, the boundary layers from opposite walls meet at the center, and at that point, the flow is said to be fully developed. We can estimate how far the fluid needs to travel before this fully developed state is reached using the hydrodynamic entry length. For laminar flow, the entry length is roughly 0.05 times the Reynolds number multiplied by the diameter. For turbulent flow, it's about 10 times the diameter of the pipe. Once fully developed, the velocity profile no longer changes with distance along the pipe. It becomes stable and predictable, an essential condition for many engineering calculations involving pressure drop, friction factor, and flow rate. 4. Laminar flow in pipes. When flow inside a circular pipe is laminar, its velocity profile isn't flat, it's parabolic. That means the fluid travels fastest at the center and slows down toward the walls due to viscosity. Mathematically, the velocity as a function of radius is given by u of r equals 2v average times 1 minus r squared divided by r squared, where v average is the average velocity, r is the radial position, and r is the pipe radius. At the center line, where r equals 0, we get the maximum velocity. This turns out to be twice the average velocity, or u max equals 2v average. This relation helps visualize how the fluid layers slide over one another smoothly in a laminar regime. Now, let's talk about pressure. In laminar pipe flow, pressure drops linearly with distance due to viscous resistance. The expression for this pressure drop is delta P equals 32 mu LV average divided by d squared, where mu is the dynamic viscosity, L is the pipe length, and d is the diameter. To determine the flow rate, we use the famous Hagen-Poiseuille equation. Q equals pi d to the fourth delta P divided by 128 mu L. This formula shows how sensitive flow rate is to diameter. It scales with the fourth power of d. That's why even small changes in pipe size have a big impact on volumetric flow. This slide highlights how elegant and predictable laminar flow can be, especially when dealing with low Reynolds number systems like blood flow in capillaries or oil in microtubes. 5. Turbulent flow in pipes. When flow transitions into the turbulent regime, everything changes. The fluid no longer moves in smooth, orderly layers. Instead, it churns and swirls with chaotic eddies that enhance mixing. This leads to a velocity profile that's much fuller than in laminar flow. It's not parabolic anymore. Most of the fluid moves fast, even near the walls. Since turbulence is so complex, we rely on empirical relations to describe the velocity profile. Close to the pipe wall, we use the law of the wall. U plus equals 5.75 log of y plus 5.5. Here, U plus is the friction velocity, y is the distance from the wall, and nu is the kinematic viscosity. This formula helps us capture the behavior of fluid right next to the boundary where velocity gradients are steep. In the core of the pipe, the flow follows a power law profile. The velocity at any point is a function of the radius given by u divided by u max equals 1 minus r divided by r to the power of 1 divided by n, where n varies depending on the Reynolds number. To calculate pressure drop, we turn to the Darcy-Weisbach equation. Delta P equals F times L divided by D times rho V squared divided by 2. The friction factor F encapsulates how much resistance the turbulent flow encounters. It's not constant. It depends on Reynolds number and pipe roughness. That's where the Colebrook equation comes in. It's an implicit equation that relates the friction factor F to both the relative roughness, epsilon divided by D, and the Reynolds number. Solving it often requires iteration or using the Moody chart. In turbulent flow, energy losses are higher, but so is mixing efficiency. That's why it dominates in most practical engineering systems, from power plants to pipelines. 6. Minor losses. When analyzing fluid flow through pipes, it's not enough to consider friction losses along the length of a straight pipe. Real systems have bends, valves, fittings, expansions, and contractions, and each of these introduces what we call minor losses. But don't let the name fool you. These losses can be significant, especially in short piping systems with many components. Minor losses are quantified using a loss coefficient, denoted as KL.
The head loss associated with a particular fitting or disturbance is calculated using the formula HL equals KL times the velocity squared divided by 2g, where v is the velocity of the fluid and g is gravitational acceleration. Each component has its own characteristic KL value based on experimental data. For example, an open gate valve has a loss coefficient of about 0.2. A 90-degree elbow causes more disruption and thus has a higher value, around 0.3. In cases of sudden expansion, flow separation occurs, and the loss becomes a function of area ratio. The corresponding loss coefficient is given by KL equals 1 minus d squared divided by d squared squared, where d and d are the diameters before and after expansion. The more abrupt the change, the higher the loss. Understanding and accounting for minor losses is crucial in pump selection and energy efficiency calculations. While they're called minor, their impact can quickly add up, especially in complex piping networks.
7. Piping networks. When dealing with complex systems, we rarely encounter a single straight pipe. Instead, we often see a network of interconnected pipes, some arranged in series, others in parallel. Understanding how flow behaves in these networks is critical for accurate system design. In a series configuration, all pipes carry the same mass flow rate. The fluid travels through one pipe and then directly into the next. While the flow rate remains constant, the energy losses accumulate. That means the total head loss is simply the sum of all the individual losses, HL equals sigma HLI. Each bend, valve, or pipe segment adds to the total resistance the fluid must overcome. In contrast, a parallel configuration splits the flow into multiple branches. Here, the pressure drop across each branch must be the same because the ends are connected to the same upstream and downstream points. The total flow rate through the system is then the sum of the flow rates in each branch. Q total equals Q1 plus Q2. This setup allows us to distribute flow based on resistance, with lower resistance paths carrying more fluid. These simple principles, constant flow rate in series, constant pressure drop in parallel, form the foundation for analyzing water supply networks, district heating systems, and even complex HVAC layouts. Get these basics right, and you'll be able to model real systems with confidence.
8. Pump selection. Selecting the right pump isn't just about choosing a powerful machine. It's about matching the pump's performance to the system's actual needs. To do that, we start by calculating the total head the pump must overcome. That includes both the head loss from friction and fittings and the elevation difference between the source and destination. Mathematically, we express this as H pump equals HL plus Z2 minus Z1. Once we know the required head, we assess pump efficiency. Efficiency tells us how effectively the pump converts mechanical shaft power into fluid energy. It's defined as eta pump equals W fluid divided by W shaft. A higher efficiency means less wasted energy and lower operating costs. But the most critical concept in pump selection is the operating point. This is the point where the pump's performance curve intersects with the system curve. The pump curve tells us what the pump can deliver, while the system curve tells us what the system demands at different flow rates. Their intersection gives us the flow rate and head at which the pump will actually operate. Get this intersection wrong, and you might end up with a pump that's too weak to deliver the required flow, or one that wastes energy by overshooting system needs. That's why understanding the pump-system relationship is essential for reliability, efficiency, and longevity of your fluid system. 9. Flow measurement devices. Knowing how fast or how much fluid is moving through a pipe is fundamental in fluid mechanics. That's why we rely on flow measurement devices, tools that translate pressure, velocity, or physical movement into usable data. One of the most straightforward methods is the pitot-static tube. It uses Bernoulli's equation to calculate velocity based on the difference between static and stagnation pressures. Simple, effective, and widely used in both labs and airplanes. To measure flow rate rather than just velocity, we turn to devices like orifice meters or Venturi meters. These use the pressure drop caused by flow constriction to compute the volumetric flow rate. The equation includes a discharge coefficient and accounts for the geometry of the restriction. They're compact and commonly used in industry. Rotometers are another approach. These are variable area flow meters where a float rises in a tapered tube in proportion to flow rate. They're great for visual and real-time flow indication, especially in low-tech setups. For non-invasive and high-precision applications, ultrasonic flow meters are ideal. They measure the Doppler shift in sound waves to determine how fast the fluid is moving. No moving parts, no insertion, just sensors on the outside of the pipe. Then there are turbine flow meters. These work like mini windmills placed in the flow. The fluid spins the blades, and the rotation rate correlates with the velocity. They're mechanical, robust, and suitable for clean liquids. Each device has strengths and limitations. Your choice depends on accuracy needs, fluid type, installation constraints, and budget. But the core idea remains. If you can't measure the flow, you can't manage the system.
10. Key takeaways. Let's wrap up this chapter on internal flow by zooming out to see the big picture. At its core, internal flow is driven by pressure differences within completely filled conduits. Unlike open channel flow, internal flow operates in a closed environment, where friction and boundary effects dominate. We learned that head losses come from two sources: major losses caused by pipe friction and minor losses caused by fittings, valves, bends, and changes in geometry. Both types of losses reduce the system's efficiency and must be carefully calculated. In piping networks, we apply conservation principles. For pipes in series, the flow rate stays the same while the losses accumulate. In parallel branches, the pressure drop remains constant while the total flow divides among paths. Pump selection isn't guesswork. It requires matching the system's needs with the pump's capabilities. This means calculating the total head and using the pump curve to find the operating point that maximizes efficiency. Finally, we explored different flow measurement devices, each tailored to specific applications. Whether it's a Pitot tube, a Venturi meter, or a Doppler-based ultrasonic sensor, accurate flow measurement is essential for control, diagnostics, and optimization in fluid systems. These principles aren't just theoretical. They're applied every day in pipelines, power plants, chemical processes, and HVAC systems. Mastering internal flow equips you with tools to design, diagnose, and improve the systems that move fluids through our modern world.